Students, welcome to All 4 e-learning program. This is physics session number 42. Now in this session we will learn about the influence of the cavity in a metal conductor. Now what happens if there is cavity inside a metal conductor? What are the various effects? Let's have a clear idea regarding this, right? So before going to it, let's have a glance of what are the things required for it. So I was telling you, whenever a charge is a fundamental quantity, every charge produces field has lines of force, right? And the field has strength, electric field strength, electric field intensity E, right? And the electric flux is the measure of number of lines of force. Flux is E dot A. For uniform electric field it is E dot A. For non-uniform electric field it is d phi E dot ds. The total flux is the integral, the surface integral of E dot ds. According to Gauss law, the total flux through a Gaussian surface is the charge enclosed inside by epsilon naught. Well, we'll be making use of these things while understanding the concept of the cavity in a conductor. So what happens if there is a hole or a cavity inside a metal conductor? Suppose there is a metal conductor like this with a cavity inside. So this is empty space. You know, in the previous session we have learned, whenever charge is given to a metal conductor, charge resides only on the surface, right? Whenever I give charge, suppose if I give positive charge, now these two like charges repel, so now they get repelled and they move to the extremities and they exist only on the surface. They move to the extremities of that conductor and they reside only on the surface. So when they reside, the charge is residing only on the surface. Now we have even learned charge exists only on the surface. So the charge inside the conductor is zero. No charge resides inside the conductor. So when there is no charge inside the conductor, the flux originating from any Gaussian surface inside is zero. And the electric field at any point inside is zero. So inside there is no field. So field inside is zero. Therefore, then there will be no charge that is pertaining to this cavity even. Neither the inner part of the inner surface of the cavity, nor there is no influence of this charge with respect to the cavity. So there is no charge pertaining to the cavity. Now this you can prove by considering a Gaussian surface around it. Let me imagine a Gaussian surface, right? Now small flux is E dot ds. The small flux, right, is E dot ds through this small area element. The total flux through this Gaussian surface is integral E dot ds. Well, this is equal to, according to Gauss law, charge inside by zero. Charge that is residing inside by zero. But we know that there is no field at any point inside the metal conductor. So the electric field inside the metal conductor is zero. So charge inside by epsilon naught is zero. So the charge inside the metal cavity is also zero. So even when there is a cavity inside the metal conductor, when you give charge does not go inside the thing, right? It doesn't mean charge, right? The main intention in giving you this concept is, when I give charge, the charge doesn't go inside and stay inside the conductor, right? That doesn't happen. So even when there is a cavity, like this, right, then charge never goes inside. Charge exists only on the surface of the conductor. For example, let us say there is a metal slab like this. I give charge, where I am giving charge like this, right? Then suppose if it is a long metal slab, for example, let's suppose it is a long metal slab, right? Then charge. Now if this metal slab is bent to enclose, if the charge is bent to enclose, then this surface gets the inner point. It forms a cavity. There will be no charge inside. So the main intention in giving you this idea is, even though there is a cavity inside the metal conductor, there will not exist any charge inside. The charge given goes to the outer surface, not to the inner surface. Charge inside the cavity is always equal to zero. Achha, what will happen if I place a charge inside the cavity? So better understand, whenever a metal conductor with a cavity inside is given a charge from outside, right? I am giving charge. It is electrified by conduction process or whatever process. Then the charge given to it will reside only on the outer surface of the conductor. No charge will go inside, and no charge will reside inside the cavity also. No charge will exist. No charge will exist on the inner surface of the cavity also. So there is no charge pertaining to the cavity. Okay, right. Suppose there is a conductor with no charge. There is no charge. There is a cavity inside the conductor, a hole inside the conductor. Now I place a charge at the center of the cavity, positive charge at the center of the cavity. Then what happens? So when I place a positive charge at the center of the cavity, now this positive charge produces its lines of force, and these lines of force start from this positive charge and they terminate they stop at the inner surface of the cavity. They stop at the inner surface of the cavity like this. In the sense, when positive charge is placed at the center, then on the inner surface of the cavity, negative charge, equal and opposite negative charge is produced. On the inner surface, minus Q charge is developed. So the lines of force from the positive charge, they originate here, they terminate here. You know, we have been learning from positive charge, the lines of force emerge from the positive charge outward. For negative charge, the lines of force terminate and stop. Come from infinity, terminate at the negative charge. So these lines of force are terminating on the surface. In the sense, negative charge is produced. There is negative charge that is produced. Now how can you prove that there is negative charge produced? You can prove this by Gauss law. Let me imagine a Gaussian surface. Let me imagine a Gaussian surface over this cavity like this. Right? This Gaussian surface is now lying over the cavity in the metal conductor. Right? This is the cavity. This is all metal. This is all metal space. It's all metal body. Right? It's all the metal body. Right? All metal body. So this is the cavity. I have placed the charge inside the cavity. So what happened is the lines of force originate from the positive charge. They terminate at the inner surface. Stop. So negative charge is influenced. How can you prove that there is negative charge influenced? Now consider a Gaussian surface above the cavity which is in the body of the metal conductor. Right? Let us calculate the flux by Gauss law. We know the electric flux due to the total flux from the Gaussian surface is the net charge inside by epsilon naught. The total charge that is enclosed inside by epsilon naught. So the total flux is, but according to the definition of electric flux, it is the surface integral of E dot ds. Now, if the electric field here is E, if I imagine a small area element ds, electric field is E, then the total flux by definition, according to the definition, the total flux from the Gaussian surface is integral E dot ds, and this is equal to the charge enclosed inside by epsilon naught. But you know, we have studied earlier, at any point inside the body of the metal conductor, the electric field at any inside point is 0. Now our Gaussian surface is inside the body of the metal conductor. So at every point on this Gaussian surface, the field should be 0. So that every point the electric field is 0. So this is 0. So charge inside by epsilon naught is 0. But I have already placed a point charge Q here. We don't know. Let the charge on the inner surface be X. So the total charge inside the Gaussian surface is plus Q plus X by epsilon naught. This flux is 0. Well, this is 0. Q plus X is 0. So X is minus Q. So an equal and opposite negative charge is induced on the inner surface of the cavity. This is the proof. There will be equal and opposite charge that will be induced at the inner surface of the cavity. So the lines of force originate here, they terminate here. At any point inside is 0. Now what happens on the surface? Because of this, what happens on the surface of the conductor? Now when you come to the surface of the conductor here, now here then an equal amount of positive charge appears on the surface of the conductor. There appears whatever charge that you have placed at the cavity there, then equal charge is produced on the surface. How can you prove that there is equal charge that is produced on the surface of the conductor? Imagine a Gaussian surface. Imagine a Gaussian surface, right? Then the total flux originating from this Gaussian surface is the charge that is enclosed inside by epsilon naught. Now there is a charge inside, positive charge inside there, so there must be some net flux coming out. So the net charge inside. So we have already proved that there is a point charge, an equal and opposite charge on the inner surface. We don't know the charge x on the outer surface, right? So therefore, the total charge that is, we have placed a point charge q. So the total charge inside the Gaussian surface is point charge plus q. The charge that is residing on the inner surface minus q plus x. This is equal to the net flux. The net flux is charge that is enclosed inside q. So x is equal to plus q. So let us not think about this metal body. I have placed a positive charge, right? Consider the Gaussian surface of the outer surface, on the outer part of the metal body, that there is a charge, point charge inside. So the flux should be due to point charge. So flux is charge q by epsilon naught. But this is plus q. On the inner surface there is minus q. We don't know the charge that is on the outer surface. Let it be x. So plus q minus q plus x. The net flux according to Gauss law. But this is nothing but q by epsilon naught. So plus q minus q, this and this cancel, then the outer charge, all the charge appears on the outer surface. So whenever a charge is placed at the center of the cavity, then an equal and opposite charge is induced on the inner surface of the cavity, and an equal positive charge is induced on the outer surface of the metal body. But at any point on the inside point here, the net resultant electric field is 0. There will exist no charge, no flux, no charge at any point in the metal body of the metal conductor. The electric field strength will be 0 inside. At any point inside field is 0. So plus q will induce minus q on the inner surface and plus q on the outer surface. You see the net charge inside. This is plus q here. This is plus q. This is minus q and plus q. The net charge inside is q. Okay, thank you. Yes. So whenever there is a charge inside the cavity there, then positive charge, equal and opposite negative charge is induced on the inner surface, and the equal positive charge is induced on the outer surface. Now I have placed charge q. According to law of conservation of charge, the total charge must be constant. So initially I have taken a metal conductor with no charge. Then there was a cavity. I placed a charge plus q here. So I have considered a charge plus q. So if I take the total charge with respect to system, the total charge with respect to system must be q. Total charge with respect to system must be q. But this is plus q which I placed. Minus q was induced on the inner surface, and some x charge is produced on the outer surface. Then the net charge should be, according to law of conservation of charge, whatever charge I have taken. I have taken a charge q. So the net charge of the system, it's plus q that is placed at the center, minus q that is induced on the inner surface, plus x on the outer surface. Well, these two get cancelled. X outer is q. Right? So this way, whenever a charge is placed at the center of the cavity, then what happens? Now an equal charge appears on the inner surface, and equal and opposite charge appears on the inner surface of the cavity, and equal identical charge is produced on the outer surface of the metal conductor. Okay, now what happens if this charge is not at the center? If I displace this charge, instead of here, if I place the charge somewhere here, then what happens? Then the lines of force will exist in such a manner. Again, they originate and terminate on the walls of at the inner surface of the cavity. Again, same minus q charge will be induced. Same Gauss law. Because the charge, whatever charge that is placed inside, produce an equal and opposite charge such that the net electric field at any point inside the metal body is 0. So field 0, if I imagine a Gaussian surface, the net flux should be 0. So the total charge should be 0. So if it is plus Q, but minus Q. But the charge distribution takes place in such a manner that at any point on the metal body, inside the metal body, the field is 0. Well, again the positive charge is produced here. Positive charge will be appearing on the outer surface with respect to this positive. Same positive charge will be coming out, and the lines of force emerge normally from the surface of the outer surface of the metal body like this. So even when the charge is not at the center, the charge distribution takes place in such a manner. The charge distribution on the inner surface of the cavity will change such that the net electric field at any point in the metal body is 0. But on the outer surface there is no change. The lines of force emerge like this. Acha, what will happen if there is already charge on the conductor and if I place a charge at the cavity of the conductor? Suppose, consider a metal charge. Already it is possessing a charge, let's say Q0. It is possessing a charge Q0. It is having a cavity. Now I place a charge plus Q at the center of the cavity. Then what happens? Same thing. The lines of force originate here, terminate at the inner surface of the cavity. They start here and stop here, inner surface of the cavity, plus Q. So minus equal and opposite charge appears on the inner surface of the cavity. Minus Q appears in the inner surface of the cavity. Because the net, if I take a Gaussian surface at any over the cavity at any point in the metal body there, the net, we know the net electric field strength in the metal body is 0. So the net flux should be 0. If the net flux is 0, the total net charge inside should be 0. But there is a point charge being placed, so an equal charge is induced. Then when there is negative charge here, according to conservation of this thing, so now an equal positive charge will appear on the outer surface of the metal body. Outer surface of the metal body, an equal charge will appear. So the net charge of the metal body will be Q0 plus Q. Because according to conservation of charge, I first have considered a metal body with a charge Q0. Later I placed a point charge plus Q at the cavity. So I have considered a total charge Q plus Q0. So with respect to the total system, the net charge should be Q plus Q0. Now, what is the net charge of the system? A point charge plus Q. On the inner surface, it is minus Q. The total charge on the outer surface is plus Q. Right? Then this must be equal to Q0 plus Q, according to conservation of charge. So the X on the outer surface is Q0 plus Q. So whenever you place a charge inside, an equal charge, identical charge appears on the metal surface. Equal and identical charge will appear on the metal surface there. Now, similarly, suppose if I displace this, what happens? If I displace this here, instead of center, if I place here, then what happens? The charge distribution on the inner surface of the cavity will change. Well, because it is nearer, maybe more charge is deposited here, less charge. But the charge distribution changes of the inner surface changes such that the electric field at any point in the metal body is here. Well, the total charge Q appears there, same. There is no change in the charge distribution on the outer surface. Only on the inner surface there is variation. Right? If I displace this, then on the inner surface of the cavity, charge distribution changes. The total charge is same, minus Q. The distribution of charge will change such that the net electric field at any point in the metal body is 0. The total charge on the outer surface remains plus Q or minus Q. Achha. Next point. Now what will happen if consider a metal conductor with a cavity. right, with a cavity. Now I have placed this in a external magnetic field. If I place it in an external electric field, in an external electric field, due to the electric field, charge will be induced on it. Now the charge that is induced will again stay only on the outer surface, but no charge will be induced inside the cavity due to the external instead of external field. Let's say if I place a point charge at the outside, because of this, charge will be induced in this. Now next, let us calculate the electrostatic mechanical force on the charged conductor. When a metal conductor is charged, what is the force, the electrostatic pressure experienced? Let's deduce a formula for it. Look here. Consider a charged sphere, right? Let there be a conducting sphere. I am giving charge to it. So when charge is given to it, when I give charge, the charge is uniformly distributed over it. Let the charge be Q. Its surface charge density is sigma, right? Now, like charges repel one another. When I give charge, so each charge has influence on the other. So every charge on this conductor is repelled by all the remaining charge on the conductor. So every element experiences force. There is a force experienced due to the charge that is present on it. So let us deduce a formula for the mechanical force that is experienced by it. Okay. Let us consider a small area element here, area element ds. A small area element ds here, this part. So the small charge that is residing on this area element, let it be dq. So the small charge on the area element is dq. We know surface charge density is surface per unit area. So cross multiply, charge is sigma into ds. Equation 1. Now we know, consider a point P very close to it here. Point P very close to it. Now the net electric field here is due to the small area element, that is E1, plus the electric field due to the remaining charge that is on the conductor, E2. Consider area element like this of area ds. The small charge on this area element is dq. Imagine a point P very close to it. Now, the net electric field at this point P is the electric field due to this small area element plus the electric field due to all the remaining part of the charged conductor. So, let the field due to the small area element be E1. And the field due to the remaining part on the conductor be E2. Both are in same direction. So the net field is E1 plus E2. Let me imagine a symmetrical point opposite to point P here. Let it be P dash inside the metal conductor. Even there also the field due to this part is E1 and the field due to remaining part of the charge conductor be E2. Right? So when I take this small element, when I consider the element, field at either this side or this side, field produced by this sheet at this point or this point on either sides must be same. So this is a small area element. Field produced by it at this point P, this side is E1 and this side is E1. Now the remaining part of the sphere, this one, that remaining part, even that remaining part also produces field here. This is E2 and this is E2. But this point P is outside the sphere and this point P dash is inside the sphere. This point P is outside the sphere and this point P is inside the sphere there. Right? So therefore, now considering the field, so the field due to element is E1 and due to the remaining part is E2. Now we know outside point, the net electric field is E1 plus E2. So we know E1 plus E2 is equal to, we know for a metal sphere at the nearest point, the field is sigma by epsilon naught. At the nearest point to the metal conductor, the electric field is sigma by epsilon naught. Now at this inside point, now these two fields will be in opposite direction. So E1 minus E2, let's take the magnitude, right? So E1 minus E2, now this is 0. This is 0. We know at any point inside the metal conductor is equal to 0. So both should be equal and opposite. It is 0. So when I add both, this gets cancelled. 2E1 is sigma by epsilon naught. So E1 is equal to sigma by 2 epsilon naught. Right? Field due to this or field on it. So therefore, the field produced. So the electric field, net electric field on the outer surface, nearest point on the outer surface is sigma by epsilon naught. So at this point P, the field due to this area element is E1 and field due to the remaining part is E2. Right? So therefore, both are in same direction. So E1 plus E2 is, we know the formula sigma by epsilon naught. But at the inside point P dash, the net electric field is 0. Field due to this area element is E1 and field due to the outer, the remaining part of the sphere, it is E2. Both are in opposite direction. So the net field is 0. Adding both, 2E1 is sigma by epsilon, E1 is sigma by 2 epsilon. But E1 minus E2 0. But E1 is equal to E2. So E2 is also equal to sigma by 2 epsilon. So at the nearest point on the conductor, field produced due to the remaining part of the conductor. Suppose if I take this conductor, this was the small area element. So at the nearest point, the field produced by the remaining part of this conductor, this remaining part from here to here, this part, right here, it is E2 sigma by 2 epsilon naught. Now, the field that is produced near this area element which we have considered, that field E2 is sigma by 2 epsilon naught. Now that field will act on this area element. Now the force experienced by that area element, the force that is experienced by the area element. We know force, I am considering this as a point charge. It's a small area element, so it's almost a point charge. So the force experienced by a point charge in the electric field, F is equal to EQ. So the force on the area element is the electric field that is produced by the remaining part, that is E2, into the small charge dq. But you know, we have already found dq is sigma ds. So the force experienced by that small area element, charged area element, it is E2. E2 is sigma by 2 epsilon naught into sigma by 2 epsilon naught into ds. So that ds is sigma, dq is sigma ds. So the force F is equal to sigma square by 2 epsilon naught ds. Now getting that ds down, force per unit area, pressure, the electrostatic pressure, it is sigma square by 2 epsilon. It is sigma square by 2 epsilon naught. But you know, if the electric field due to this sphere is E is sigma by epsilon naught. If I cross multiply, sigma is E epsilon naught. If I substitute here, the electrostatic pressure experienced by the metal charge conductor is sigma square by 2 epsilon naught. Well, sigma I can substitute as E epsilon naught. So it is E epsilon naught whole square. So it is E square epsilon naught square by 2 epsilon naught. 1 epsilon gets cancelled. Half epsilon naught E square. This is the electrostatic pressure experienced. Whether the area element is here or here, suppose if I take the small area element right at this point. So this small area element has a small charge dq, sigma ds. Then the force experienced by this area element, F is EQ. The force on it is, force on this is due to the field that produced by the remaining part of the charged conductor. So force on this area element is due to the field produced by the remaining part of the charged conductor, that is E2 into its charge dq, E into EQ. Well, the field produced by the remaining part E2, we have found it as sigma by 2 epsilon naught. So it is sigma by 2 epsilon naught into dq, but the charge dq is sigma ds, sigma into ds. So sigma square by 2 epsilon naught ds. So force per unit area is pressure. So the electrostatic pressure experienced by any area element, consider any area element at any area, the electrostatic pressure experienced is sigma square by 2 epsilon naught. It is sigma square by 2 epsilon naught, or if you know the electric field, due to this charged conductor, the electric field on the surface, nearest point on the surface is E epsilon. E is equal to sigma by epsilon naught. Substituting that, then we get half epsilon naught E square. So the mechanical force or the electric pressure experienced by any area element on the conductor, now that force F is equal to half epsilon naught E square ds, where ds is the area element. If I get the ds this side, then this is the electrostatic pressure. Half epsilon naught E square, or it is sigma square by 2 epsilon naught. A very important formula. Electrostatic pressure experienced by any area element on a metal charged conductor. Thank you.